Let's talk about Pascal's principle as well as Archimedes' principle. Pascal's principle states that if you have two containers connected together by a channel, such as through a tube, the fluid will flow back and forth until both chambers share the same exact pressure. Now, this won't be true in real life, and I'll use a balloon as an example. With a balloon, you may believe that the pressure inside the balloon is uniform throughout, but in reality, the pressure at the top of the balloon is actually slightly less than the pressure at the bottom of the balloon. And that has to do with the fact that we're here on Earth, where gravity will pull onto the gas molecules inside the balloon, drawing them closer to the bottom of the balloon. That's why the density at the bottom of the balloon will be just a bit greater than the density at the top of the balloon. But for our purposes today, let's not worry about that. Instead, we know that pressure is also equal to force over area, so we can rearrange the formula to look like so. Let's go through a few visual examples. Let's say that we have two identical syringes and they're connected together by a tube. The gas will flow between these two syringes until pressure number 1 matches up with pressure number 2. Moreover, if we try to compress the fluid in piston number 1, the fluid's pressure will increase and will want to flow into piston number 2. In fact, under these ideal circumstances, you'll notice that the displacement of piston number 1 works out to the same displacement as piston number 2. After all, these are two identical syringes. The pressure inside the chamber is trying to match up with the pressure in the outside environment, and it's working out beautifully in this case over here. Let's change it up a bit. Let's say that we connect the smaller syringe to a much larger syringe with a larger piston. As we compress the fluid in the first piston, the fluid will want to find its way into the second chamber such that pressure number 1 will match up with pressure number 2. Now, since the surface area of the second piston is much larger than the surface area of the first piston, and volume is equal to surface area times height, or pi r squared times h, that's why the displacement of the second piston will be a lot less than the first piston. But in both these cases, it's a situation where the pressure inside wants to match up with the pressure of the environment. And this situation will always happen as long as you have an uncompressible fluid, such as oil. But what if you did have a compressible gas? Well, then one of these two outcomes can occur. Either the second piston does not displace as much, or the second piston may not displace at all. That's a problem with regards to gases. They can change shape very easily and not be in the same volume. In both of these circumstances, the pressure inside will be greater than the pressure of the environment. In fact, if we let go of the first pistons, they will restore to their original length. Let's go through a numerical example. As we know, cars are very heavy. In fact, without adrenaline, it's pretty much impossible to lift a car with one human being. However, if we use a hydraulic lift, then this exercise isn't as challenging. Let's use these numbers over here. One thing to keep in mind is that the surface area of the piston works out to pi r squared. So when we look at the first formula, we need to replace A with pi r squared. The weight of the vehicle, F2, is m times g. So when we calculate it out, we'll find out that the force required in order to lift this car works out to roughly the weight of the mechanic himself or herself. In the setup over here, we'll notice that it's 17 times easier to lift the car using a hydraulic lift. So we have a 17-to-1 mechanical advantage. There is a catch, however. Even though it is 17 times easier to lift the car, the travel through the first piston will also be 17 times longer. In other words, if the mechanic so happens to depress the piston at a distance of 1.5 feet, the car will only rise about an inch. Archimedes' principle can be used to explain why a boat can float in water. A boat will actually displace as much water as the weight of the boat itself along with all of its contents. And once it does that, then we have a static equilibrium, where F net y is equal to 0, or the buoyant force works out to the weight of the boat and all of its contents. If we actually look into the buoyant force in more detail, the formula for buoyant force works out to the density of the fluid times the volume of the fluid displaced times the gravitational field strength. So whatever planet you may happen to be on will have an impact on the buoyant force. Another variable that can impact the buoyant force is the density of the fluid. You may have seen vacation pictures of people easily floating on the Dead Sea, and that has to do with the fact that the Dead Sea is comprised of salt water, which is more dense than body fat. As a result, the buoyant force will be greater than the gravitational force of the human being, and people float in the sea. You may have seen this YouTube video before. It's a story of a professor filling up an aquarium with an invisible gas, which so happens to be sulfur hexafluoride. Now, contained inside the boat is regular atmospheric air. And atmospheric air is about 5 times lighter than sulfur hexafluoride. So if you happen to fill up the boat with sulfur hexafluoride, since aluminum is more dense than sulfur hexafluoride, the aluminum itself will still sink. Another mathematical example. Let's say that you accidentally drop your physics textbook in a swimming pool. Question is, will it float? Few things we need to keep in mind. First off, volume needs to be calculated out in cubic meters. So we need to multiply 0.2 meters by 0.3 meters by 0.05 meters, which works out to 3 times 10 to the negative 3 cubic meters. The density of water is roughly 1,000 kilograms per cubic meter, or at least that's the value at 4 degrees Celsius. Now the textbook will float in the water as long as the buoyant force matches up with the force of gravity. So let's calculate them out separately. The buoyant force works out to 29 newtons. So we're multiplying the density of the water times the volume of the water that's been displaced by the textbook times the gravitational field strength. When we compare it to the force of gravity is much greater than the buoyant force. As a result, the textbook will sink. There is one advantage, though, of having a textbook inside water as opposed to on land. If you've ever tried lifting up a person in water, you'll notice that it's much easier to carry a person, and that has to do with the fact that the water provides a buoyant force, making your effort a lot less. So this textbook will actually feel a whole lot lighter in water than on land. In fact, the textbook will feel as if it's only 19 newtons heavy as opposed to 49 newtons heavy. Archimedes has a very interesting story. Legend has it that the king once received a crown, and the king wanted to know whether the crown was made up of real gold or fake gold. So he summoned up Archimedes to figure it out. There was a catch, though. Archimedes was not allowed to deform the crown and convert it into a block so that he could figure out the density of the crown. So Archimedes sat down and thought about it while he was taking a hot bath. Back then, it was well known that the density of gold was roughly at 20,000 kilograms per cubic meter. And if you so happen to submerge that gold in water, the gravitational force acting on the gold will outwin the buoyant force. As a result, the gold will sink. However, the weight of the gold will not feel as heavy in water. So you could actually use a scale to figure out that additional net force to be able to suspend the gold in water. So if we add the buoyant force with the force of the scale in lifting up the gold, it should match up with the weight of the gold itself. And while it's suspended, F net works out to 0. Buoyant force works out to the density of the water times the volume of water that's been displaced due to the crown itself times the gravitational field strength. Now we don't really need to figure out what the mass of the crown is because we know that mass times gravity gives us weight anyways. So if we take this equation and we rearrange it and isolate for the density of the object, we can determine whether or not if that crown was made up of gold or something else. When Archimedes figured this out while he was taking a hot bath, he jumped out of the tub, ran around town in his birthday suit, and shouted for joy, "Eureka!" which in English means, "I have found it." He has discovered a way to figure out whether the crown was made up of gold or something else, without destroying it. You may have heard from the legends of Titanic that only about 10% of the iceberg is visible above the water. So let's calculate that out. We're going to compare the density of the ice itself versus the density of salt water, which is at around 10,000 kilograms per cubic meter. In order for the iceberg to float, the buoyant force must match up with the force of gravity. This does not mean that we need the entire iceberg to be submerged in the water, only a portion of it. So we found out that the buoyant force works out to density times volume times gravitational field strength, or surface area times the height of the iceberg that has been submerged. So that's what H is, the amount of that the ice is in the water. And we know that the weight of the iceberg itself is equal to mass times gravitational field strength. When we equate these two equations together, we find out that only about 27 centimeters of this ice cube has been submerged in the water, leaving roughly 3 centimeters above the water. So how much water is needed to float a boat? In reality, not much at all. In fact, the boat only needs to displace as much water as the weight of the boat itself. So a channel that's roughly the same shape as the boat itself, the boat can easily sail through. Obviously, we want to give a bit of clearance as the boat will sway back and forth, but we really don't need much water at all. Here's another crazy question. How much water is needed to dive into a pool?
The real big trick with this dive is to land flat and try and get as much water out of this pool as I can. I want to dissipate as much water for a cushion effect.
Let's talk about the science of how balloons work. Now, if you fill up a balloon with a very light gas such as helium, it will have the tendency to want to rise. But if you place it in outer space, it'll have a tendency to want to expand because there's nothing holding it in its place. In fact, if the balloon isn't strong enough, it might pop. So the reason why a balloon will retain its particular size is because it's here on Earth, squishing it back down to the size that we see it. The Earth, however, does love the atmospheric air more than the gases inside the balloon itself, because atmospheric air is much more dense than the gas inside the balloon. So it'll be drawn downwards, and just like trying to squish toothpaste out of a toothpaste tube, the balloon has nowhere else to go but upwards. And that's why balloons rise. Let's go through a mathematical example. Let's say that I want to be swept off my feet using just balloons. How big of a balloon do I actually need? Here's a few constants, and we know that the density of helium is much less than the density of atmospheric air. When we deal with the free body diagram, we know that the only way for me to float is if the buoyant force was greater than the force of gravity. And don't forget that the force of gravity is acting on not only me, but on the helium as well as the mass of the balloon. So we have to factor that into our calculations. The buoyant force is based upon the density of atmospheric air, the amount of air that's been displaced due to the helium, times the gravitational field strength here on Earth. And the weight, don't forget to factor in the mass of the helium. So when you go through the math, the only way for me to float is FB was greater than FG. So the minimum amount of helium required is roughly 70 cubic meters. What does that work out to? Well, if we find out the radius of the balloon, that works out to about 2.5 meters, or a diameter of 5 meters, which is half the width of a classroom. That's a pretty big balloon. I don't know if you've ever tried this before, but the next time you have a balloon, place it in the back of your vehicle, and with a responsible adult, have the adult accelerate the vehicle, and think about which way will the balloon veer towards. Now typically we would think that the balloon would veer towards the back. After all, as a car accelerates, we get slammed against the seat, and it has to do with the fact that our bodies contain this property called inertia, or the resistance towards change in motion. So as a car accelerates forwards, we have a tendency to move backwards relative to the car. However, for a balloon, it's a completely different story. So why does this happen? Let's break it down. So while a car remains stationary, again, the Earth loves the weight of the atmospheric air greater than the weight of the balloon itself. And that's why the atmospheric air is drawn downwards, squishing the balloon to go upwards. Now, if we so happen to accelerate the car forwards, the inertia of the atmospheric air will be much greater than the inertia of the gas inside the balloon. So the atmospheric air inside the car will be squished to the back of the car, forcing the balloon to be squished forwards. And that's why when you accelerate a vehicle, a helium balloon suspended inside a car will actually drift towards the front seat. It's a pretty trippy experiment if you ever try it in the future. For more review, check out us.archive.org. I will include a link in the description below. Until our next adventure together.